Hi, my name is Michelle Bland, and along with Olatunji Ojo and Dr. Carl Lovely, our lab is exploring a novel fluoride-induced procedure to cyclize oxazolone products. Oxazolones are 5-membered heterocyclic compounds containing nitrogen and oxygen, which display marked biological activity. The specific motif is found in a variety of pharmaceutical agents, such as in certain antibiotics used to treat severe infections by gram-positive bacterial strains that are resistant to other antibiotics, such as MRSA. Rivaroxaban, which is trademarked as Xarelto, is an anticoagulant that is commonly prescribed to treat and prevent blood clots in high-risk patients. Finally, this motif is also found in certain monoamine oxidase inhibitors, which are used as treatments for depression. From these examples and others, it is clear the high versatility of this class of compounds demands further methodological exploration for their preparation. For the current project, we are developing a novel strategy to synthesize 2,3-H-oxazolones. What sets this methodology apart from previous techniques is that it uniquely utilizes a fluoride source to induce cyclization of alkynyl carbamates to the desired heterocycle product. This project was designed to begin from aldehyde precursors, which were used to synthesize propargyl alcohols using an acetylenic Grignard reagent. The propargyl alcohol product was then intended to be subjected to addition with isocyanates to furnish carbamate derivatives. Originally, our goal was to cyclize these carbamates to a 5-membered heterocycle with an outside double bond, that is, 4-methylene oxazolidinone. However, as I will discuss later, the product we obtained revealed the double bond had migrated inside the ring, as in 4-methyl oxazolone. Thus far, each synthetic step has been successful and in good yield. To begin, we subjected 3-phenylpropanaldehyde to an ethanyl Grignard reagent and obtained propargyl alcohol in 60% yield. This propargyl alcohol was then subjected to addition with phenyl isocyanate, and we obtained the carbamate derivative in 65% yield. Interestingly, when we subjected the carbamate to the fluoride source, specifically tetrabutylammonium fluoride, or TBAF, we did not obtain the desired 4-methylene oxazolidinone, but instead, we obtained 4-methyl oxazolone, where the double bond had migrated inside. However, the methylene oxazolidinone was observed in the NMR spectrum of the crude reaction mixture, though this adduct was in trace amounts. Based on these findings, we have chosen to pursue the methyl oxazolone product and are currently in the process of optimizing the cyclization reaction. To do so, we began by varying the equivalent of TBAF used while the solvent temperature, time, and atmosphere was controlled. Specifically, the carbamate was dissolved in THF solvent, put under an argon atmosphere, and placed in an ice bath before TBAF was added dropwise. After addition, the mixture was transitioned to room temperature and allowed to stir for 30 minutes while still under the argon atmosphere. Using this procedure, we realized that cyclization remained highly successful at increasingly lower equivalents of TBAF, with high yields continuing to be seen as low as 0.25 equivalents of TBAF. Based on these findings, we then began to vary the fluoride source used, and we tried cesium fluoride next. However, we found that cesium fluoride was not readily soluble in THF, DCM, or acetonitrile solvents. We tried to increase its solubility by adding 0.2 equivalents of crown ether, but we still found it to be insoluble. Thus, we began to explore the TBAF reactions in solvents other than THF and found that the reaction appears to work best in more polar solvents such as THF and acetonitrile. We also explored the effects of temperature and reaction time, but found that the ideal conditions were using THF and 0.25 equivalents of TBAF added under an ice bath and then transitioned to room temperature and allowed to stir for 30 minutes under an argon atmosphere. Under these conditions, we obtained the oxazolone in yields as high as 96%. In the future, we intend to explore even lower equivalents of TBAF, such as 0.1 equivalent. Preliminarily, we have also begun to vary different substituents from the aryl group to determine if electron density on the aryl group affects the efficiency of the fluoride-induced cyclization procedure. We began by introducing a methoxy substituent to the aryl group and subjected the carbamate derivative to cyclization. The obtained methoxy-aryl oxazolone was in 99% yield. We have also begun to explore trifluoromethyl and have obtained the substituted carbamate in 46% yield, but have not yet cyclized this product as of this presentation. To conclude, we are exploring a novel procedure to cyclize oxazolones using a unique fluoride induction technique. From the results so far, the adduct has been obtained in high yields around 95% yield, using a catalytic amount of fluoride source in a very short reaction time, increasing the desirability of this procedure based on early results. Our future work aims to explore the substrate scope of the aryl group more deeply, such as by introducing bromo, methyl, cyano, and nitro groups. I would like to end by acknowledging our sources of funding, which are the NIH, the NSF, and the Welch Foundation. Thank you very much.